So for the direct comparison test, you've got two different options. You've got these two series. A sub n is less than b sub n, or a sub n is greater than or equal to b sub n. So basically, you've got a series where a is under b. Now, if b sub n were to converge, what would that imply about a sub n? So you've got a whole bunch of bigger numbers, b sub n's, and they all add up to some number. It must mean that a sub n, which is smaller, would also add up to some number. So this would imply that a sub n also converges. And then we also have the kind of converse of this. If a sub n is bigger than b sub n, and b sub n, the smaller numbers, diverge, add up to infinity, then that must mean that the bigger numbers are also going to diverge. That implies that a sub n also diverges. Now, what you're going to do is you're going to start with a sub n, and then you're going to compare it to something like a p-test that you can tell off the bat whether it's going to converge or diverge. That's the kind of idea behind these. So you start with a sub n, you're going to compare it to something that's a lot easier to work with, and then work with it that way. Well, let's see how this looks like with a particular problem. All right, here we go. So let's say we've got number 3. What we want to compare it to is we want to look at the highest degree. This looks like a p-series for a 4. Problem is it's got that 5n. So this is our a sub n, and we want to compare it to our b sub n, which is going to be 1 over n to the 4th, and which converges. So what we need is we need a sub n to be less than or equal to b sub n. And if this is true, since b sub n converges, then a sub n will also converge. So we look at our a sub n, we have 1 over 5n plus n to the 4th. Is that going to be less than 1 over n to the 4th? Let's think about this. N's a positive whole number, so if I divide by an extra 5n in the bottom, that's going to cut the number down smaller, 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 and make it smaller than 1 over n to the 4th. So this is verified. It's true. You could do the whole cross multiplication things and get rid of n to the 4th if you'd like to, but logically I can see that this works. Therefore, a sub n converges. And you really have to cite two things. You have to cite the direct comparison test and the p-test. And the reason we cite the p-test is that's how we know that b sub n converges. If we don't have the p-test, then how would I know that b sub n converges? All right. So when we try that out with the next one, we come up with some problems. So I want to compare this to 1 over n to the 1/3, which diverges, because it's not large enough. 1/3 is smaller than 1. And I'm thinking about this, well, I'm comparing it to a p-series that diverges, so this probably is going to diverge. So for it to diverge, I need my a sub n to be greater than or equal to b sub n for me to use that. Because then if the smaller numbers were also going to diverge, the bigger numbers would also have to diverge, the a sub n's. However, is 1 over 5 plus n to the 1/3, is that greater than or equal to 1 over n to the 1/3? I don't think so, because I'm going to divide by more and more and more stuff. If you're not 100% sure, we'll do the cross multiplication just to see this one, because this one actually fails our rule. 5 plus n to the 1/3. The n to the 1/3 cancel out, and I got 0 is greater than or equal to 5. That's not true. Now, does that mean that the other one doesn't diverge? No, that just means that we failed the test, and we cannot use direct comparison test. Having that 5 in the bottom is a real thorn in our side for the direct comparison test. The direct comparison test is a very straightforward, kind of logical test, but it's not very versatile. The limit comparison test, which we'll get to next, is a much more versatile test, and that's the one we're actually going to use much more often. Almost every problem that you could use the direct comparison test for, you can use the limit comparison test and get the same answer. All right, so here's the limit comparison test. And if you have a limit of a sub n and b sub n, and they approach some number, some limit, then either both converge or both diverge. So what we're going to look at is the limit of our function or our series in comparison to a series that we know whether it converges or diverges. And we're going to look at the highest degree. So n to the third is what we're looking at here. So I'm going to compare this. I'm going to take the limit of my a sub n, which is 1 over 5 to the n plus n cubed minus 3n squared. And I really don't care about the 5n or the 3n squared. All I care about is the n to the third, because that's my degree. And we're going to divide this by a series that I know a lot about. I know a whole lot about the 1 over n to the third. So I use the same degree that I see. So whatever I would call this degree, I would call this degree -3. I'm going to divide by that. Well, when you divide by a fraction, you multiply by the reciprocal. You basically end up putting an n cubed in the top. Well, what is this limit? Well, I look at my powers. My powers are the same, and they will always be the same for these problems because you're picking them. And this limit equals 1, because I just look at my coefficients when the degrees are the same. And either they both converge or they both diverge. Well, 1 over n cubed converges by the p-series, because 3, so they converge by the limit comparison test and the p-series. Now here's where you want to be precise and still know what the answer is. So I know when I look at this, I don't care too much about these things. I'm going to compare it to 1 over n cubed. And 1 over n cubed converges by p-series. So this is one of those that I know the answer, but I still got a little work to show how I get the answer. So I know this converges when I look at it directly. Now look at 6. Well, I got to think this to be n to the 1/2. And if I take 1/2, 2 minus 1/2, I'm going to really compare this to 1 over n to the 3/2. And 3/2 is bigger than 1, so I know this is going to converge. So I'm going to compare it to this 1 over n to the 3/2, because 2 is 4/2. So if I was to ignore the 1, this is what I would get. So I'm really going to multiplying it by the reciprocal, the n to the 3/2 over 1. And we're going to take this limit of the square root of n over n squared plus 1 times this n to the 3/2. And just knowing what I know about powers, you know that this is, again, going to be n to the 3/2. They're going to cancel. I'm left with the coefficients. 1 over 1 equals 1, and they both converge. And we got to be careful, though, because 3/2 gets us into fractions, and we have to make sure that it is bigger than 1. And this converges by the limit comparison test and the p-series. Uh-oh. All right. So that's basically it. You have to figure out what you're going to compare it to. N cubed, n to the 3/2. You're going to multiply by the reciprocal because you're dividing by that actual function. You take the limit. If the limit equals a number, then they're both going to converge or they're both going to diverge. If that limit doesn't equal a number, then you picked your other series wrong. That limit should always equal a number. There's nothing for this if the limit doesn't equal a number. If the limit doesn't equal a number, then you don't know your limits very well.